till now we have been talking about various aspects of quantum computing. However, as we all know that even though computers were originally designed to do computing operation as the name suggests, over the years the use of computers have been primarily in the field of communication. Of course, the computing still remains the prime interest to scientists and engineers, but people generally use computers today to have access to the communication medium, the social media, the email, and so many other things. So, we will now be spending a bit of a time in talking about use of quantum computers as applicable for the purpose of communication. You realize, of course, that the principle of quantum computing that we have found out, like the classical computing, they are going to be common to both communication protocols and the computation itself. So, therefore, all the required things are in place. But let us look at the communication as we understood in classical regime. Of course, the simplest communication that we talk about is our talking across directly, and for people who unfortunately cannot speak, they can even use sign languages. But in any case, that's a communication. The communication, the idea is there is a person whom in our language we call usually a sender, and there is a receiver of the communication. Then we jump to a traditional telephone where there is actually a wired connection from one point to another, and something on the telephone at the sender's end or the transmitting end, as is more appropriate for this case, and the person on the other end, he can pick it up and receive whatever communication you are sending, and that will be called a receiver. Of course, over the years, this simple model that we talked about has undergone several changes. For example, an intermediate connecting wire is not necessary. If you look at the way the mobile communication works, there is a connectivity through microwave from tower to tower, and there is a relay. Now, what we want to talk about today is the process of communication as is likely to be seen in the quantum computing regime. But before we do that, let us look at the following, that when, for instance, we are writing something. Now, if I make a mistake in the spelling, there is usually no problem in understanding what I meant in spite of the spelling, because we don't really understand the meaning of every word there, but human being has this ability of assimilating the sense that is conveyed by a whole sentence. Now, this later on in the computing language came to be known as fault tolerant computing. What fault tolerant computing or communication would mean is this, that your communication protocol or even a computation should be able to withstand certain amount of errors. Now, telephone is the biggest example of that. Human speech has a wide range from 20 hertz to 20,000 hertz, but telephone equipment essentially transmits things maybe up to 5,000 hertz. But we have absolutely no problem in understanding what the person at the other end is talking about, and that is because the human hearing, it doesn't really distinguish, unless you are a very keen listener of classical music, particularly the Western variety, it doesn't really distinguish between different ranges of frequencies all that is. And this is basically the principle of fault tolerant communication, that is, the communication should be able to withstand certain amount of errors. Now, what we are going today, because the subject of errors in communication is a course by itself, but such a course cannot be complete unless I give you at least some sense of what are errors and how does one actually handle it. So this lecture and the following one I would spend on talking about errors that may arise in quantum communication in particular. Of course, I will introduce the corresponding classical thing as a reference, because of the fact that in going from sender to a receiver, the communication passes through what we will be calling as a noisy channel. Now this noisy channel introduces certain amount of errors in whatever are being sent. In our case, the bits that are being sent are subject to errors. So the first thing that we will be talking about today is how to detect errors, or in principle what are the errors, how does one detect it, and having detected it, how does one correct it. The situation in quantum computing would have its own problem, and let me begin by first talking about the way the classical errors occur and the way they are detected. So first thing that we talk about are the following, that in a classical communication a bit might just get changed. So for example, if you are sending a 0, it might become 1, or a 1 might become 0. This is because in classical communication these are the only two things that are being sent bit by bit. So therefore the only type of error that can arise in classical communication is a particular bit or several bits together will undergo change. But if you want to classify them, there are basically three types of error that we talk about. So we use the word corruption in signal to mean that receiver receives data which is different from what was sent because of noise during the transmission, and our communication protocol provides for detection of error that may arise and to take corrective steps to remedy the situation. So let us look at what are the various types of classical errors. So notice in this example that I am showing on this slide, the sender sends 10011010. The bits themselves have no significance excepting that I am giving an illustration. Now if you compare the second line with the first one, this is not very clearly visible, but there is a different color, it is a blue color there. You notice that all other bits have remained the same, but this 1 has become a 0. All other things have remained the same. This is what I would call as a single bit error. In the third line that is there, we have noticed that in the third place the 0 has become 1, and again in the sixth place the 0 has become 1. So in other words, there are two errors there. The only thing that I emphasize is these two errors are in different places, they are not adjacent, and I would call such a thing as a multiple bit error. The third type of error that occurs in classical communication is the error where consecutive bits are corrupted. So for instance, in this case the 5th and the 6th, the 1 has become a 0 and 0 has become a 1, and this is called as the burst error. So how do we detect errors? Classically the simplest would be, if the sender could tell me what he or she sent, then I would simply be able to find out what I actually got and try to see whether they are the same and take a corrective action. But there are various methods which are used to detect errors. Now one of the simplest would be, suppose the sender adds what we would call as a parity bit. The parity bit is like this, that if you have a communication of a word which let us say has 8 qubits, 8 bits, then I add another one to it. The length is not important. You could have 7 and you want to add 1 bit. But we agree on a protocol that whatever the sender sends, it has, let us say, even number of ones. Now, this additional bit which needs to be added in order to make this protocol work is called a parity bit. So notice this, that suppose I have a situation like this, 1 0 1 1 0 0 1 0. This is what was sent, let us suppose. This has 4 ones here, here, here and here. So since the number of ones is even, that is the protocol which we agreed, this is okay. This is correct situation. On the other hand, if the receiver receives a situation like this, you notice there are only 3 ones in it. So this is not acceptable. Now, in this example that I have given you, the parity bit which is, let us suppose, added at the end happens to be 0, because this was intended to be sent up to this and there are already 4 ones in it. So the parity bit could not be a 1, but what was received was something where this place, the 4th place, developed an error. So the receiver can easily recognize that this could not have been the word that was sent because it happens to have odd number of ones. The even and the odd is not important. One could agree, for example, that the number of ones could be odd, but it depends upon a protocol that we are talking about. Now, so what does the receiver do on realizing that he has received something which is not acceptable? Now, this is very simple. All that he does in classical communication is to ask the sender that can you resend it, and it is very unlikely, because remember that these are changes that occurred in the bits that are being sent because of a noisy channel, and that by definition is random. So it is very unlikely, unless you have such a noisy channel that the probability of corruption is very high, and one should not use such channel in communication. When the sender resends the message, nothing really, it is unlikely that it will be repeated. So just to make this point clear, supposing the original intended message, I will take a 7 qubit situation, supposing it was like this, 10110000. Now notice in this case, this is what was intended to be sent, but it has only 3 ones in it. Now that is not an even number, so therefore the parity bit 1 is added. Here we did not need it, we just still added a 0, because all the communications that are being sent according to this protocol would be 8. Again, I emphasize that the lengths are not important, I am giving it as an illustration. Now, you would say that this looks like a rather clumsy procedure, that we measure, detect an error, tell the sender, I did not receive what you sent. So what was done, or what is done in classical communication, is to build in what is called a redundancy. Now let us try to understand what is meant by redundancy. So redundancy is the following, that supposing you want to send a particular bit, it could be 0, it could be 1, it does not matter, but instead of sending a single bit, in its place I send multiple number of bits. Just to illustrate, I will assume that I am sending 3 bits. All that is required is it should be odd number. Now in that case I will be sending, instead of 0, I will send what I will call as a logical 0, which is defined to be equal to 0, 0, 0. 3 bits will be sent in place of 1, and likewise in place of 1 I will send the logical 1 bit, which will be then 1, 1, 1. Now in such a situation, when the communication is received, the system can automatically check by monitoring every group of 3 bits whether they happen to be identical. If they are not, then an automatic corrective mechanism can be worked out by what we call as a majority vote. This is a very simple minded procedure which says, supposing you received 0, 1, 1 or 1, 0, 1, then since this group did not have equal number of 1s or 0s, I look at what is the maximum number of, what is the identity of the maximum number of qubit bits, and in this case it happens to be 1. So I know this actually should have been 1, 1, 1 logical, which corresponds to the bit 1 which was originally intended. A very simple procedure, and it's a workable situation. And of course naturally you would think that why 3, there is nothing special, you could use 5, you could use 7, whatever it is. But the point in classical communication is that the data is constantly monitored and you have certain procedure for correcting them automatically. Now let us look at the corresponding situation that arises in quantum communication. So we assume that we have some quantum channel. So instead of sending bits 1 and 0, I am actually communicating qubits, which could be, now remember in this case, which could be in state 0, state 1, or a linear combination thereof. Now this part, that the single qubit that I am sending could be in a linear superposition of the basis state, is something which is special to quantum computers, as we have seen in the last several lectures. So in other words, there are two issues there. Supposing I want to send multiple copies of the qubit that I want, following the method that I talk about. So first thing is, of course, I am not necessarily sending 0 and 1, but I am sending a linear combination thereof. Only thing is that, can I send 3 of them instead of 1? The answer obviously is no, because we have gone through a theorem known as the quantum no cloning theorem, which says that quantum states cannot be duplicated. There is no unitary transformation which will be able to do it. So that is the first obstacle to replication of bits, as is common in classical computing, to in case of quantum computing. The other thing which makes the problem a lot more serious is, unlike in the classical case, where the receiver actually does a measurement, looks at the bits and says that I haven't received what I wanted. Whether receiver physically does that or a machine does it is unimportant. But there is something or somebody who will be looking at the bits that are sent, examine them and try to find out the correction. We have seen in quantum computing this is not feasible, because monitoring essentially means making a measurement, and the process of measurement would make the state collapse to one of the eigenstates. And so therefore this question of majority vote, etc., it doesn't quite work. So we realize by making this statement, what we are saying is, quantum states are, they have their own problems. One of the things is, quantum states are extremely fragile and are likely to, I will be introducing this word now, decohere. Decoherence means losing phase relationship. We had seen that a linear superposition of states have a certain phase relationship. For instance, simplest example is a qubit which is let us say 0 plus 1 by square root of 2, or there could be a relative complex phase between them. But supposing this 0 plus 1 by square root of 2, because of noise and interaction with the surrounding, becomes 0 minus 1 by square root of 2, then we have a problem. Now, maintaining coherent superposition of multiple qubits over a long period, long enough which is to complete a quantum algorithm, happens to be a very difficult task. The other problem is, while in classical computing the only possible error was that due to a flipping of a bit or flipping of bits, in case of quantum states there are different types of errors possible. Remember that quantum states evolve continuously. So it can introduce errors in both its amplitude and its phase, and even though such errors that are introduced during evolution could be small in magnitude, over a period of time they could build up, and that is primarily because we are not in a position to do intermediate read operations, because they all mean measurements. While having an overall phase between different components of a qubit is unimportant, because we have seen overall phase do not make any significant difference to whatever we are doing, but having a relative phase between the components in terms of basis states is important. Now, suppose I started with an initial state of, let us say, 0 plus 1 by square root of 2. And let us suppose, because of interaction with outside world, environment as we have been calling it, a relative phase was introduced between these two bits, making this, so this I will call a psi, and making this psi prime, which is, let us say, 0 plus e to the power I alpha 1 divided by square root of 2. Now, what happens if we make a measurement now? Now, if you are making the measurement of the z component, let us suppose that these represent the up and the down states of a spin, the 0 and 1. If you are making a measurement of the z component of the spin, the distribution of the eigenvalues, which are plus or minus 1, remains exactly the same. Here also the probability of getting a 0 is 1 by 2 and 1 is 1 by 2, and here it is also the same in spite of this e to the power I alpha that we have got. But suppose instead I am going to measure the x component of the spin. So what actually happens is, let me write this down in terms of my matrix notation. Remember that this is 1 over square root of 2, 1, 1. But this one is 1 over square root of 2, 1 and e to the power I alpha, which by taking out a phase e to the power I alpha by 2, I can write as e to the power minus I alpha by 2 and e to the power I alpha by 2. Now, if you measure the x component of the spin, we know that this is given by its projection operator corresponding to either the eigenvalue plus 1 or a minus 1. So let us look at what is the probability with which the eigenvalue plus 1 appears. Now for that I need the projection operator corresponding to eigenvalue plus 1, and that we know is nothing but this state, and a quick calculation shows that this is 1 by 2, 1, 1, 1, 1. This came from 2 1 over square root of 2, which is 1 over 2, 1, 1, 1, 1. So if you apply the projection operator for this, of this on psi prime, it's a trivial matrix calculation to show that this is going to give you 1 over square root of 2 cos alpha by 2 and also cos alpha by 2. Just do this matrix multiplication. So therefore, the probability with which the eigenvalue plus 1 will appear for sigma x measurement is cos square alpha by 2. So what we have seen is this, that a phase perturbation or a change in phase also is an issue that we have to worry about. The bit flip continues to be here, but loss of coherence, or as we use the phrase decoherence of a quantum state due to external perturbation, is a new thing that we have introduced. In the next lecture, we will be talking about a simple way of taking care of such errors, and we will see that while completely fault tolerant quantum computation is still probably distant in realization, there are codes available which can do error correction.